Hey everyone, welcome back to the channel. Today, I'm excited to share a breakthrough in computer science, a story about how an undergraduate student just upended a 40-year-old conjecture about hash tables. Let's start at the beginning. Back in the fall of 2021, Andrew Krapan, then an undergraduate at Rutgers University, stumbled upon a research paper titled Tiny Pointers. These tiny pointers are essentially little arrow-like markers that point you to a specific piece of data stored in a computer's memory. At first, Andrew didn't think much of it, but a couple of years later, while exploring the ideas just for fun, he discovered something remarkable. Andrew began experimenting with these tiny pointers to see if he could shrink them even further, which meant he needed to rethink the way data was organized in memory. That's when he turned to a very familiar tool in computer science: the hash table. Now, hash tables are one of the most well-studied data structures out there. They're used to store data so that you can quickly look it up, insert new elements, or delete existing ones. In a typical hash table, the time it takes to find an empty slot, especially when the table is nearly full, tends to be proportional to a number we call x, which measures how full the table is. For example, if your hash table is 99% full, you'd expect to check roughly 100 spots to find an open slot. Back in 1985, a computer scientist named Andrew Yao, who later won the Turing Award, put forward a conjecture. He argued that for certain hash tables, the best you could ever do in the worst case was to check about X positions using a method called uniform probing, essentially trying out potential spots at random. For 40 years, this idea was accepted as gospel. But here's the twist. Andrew Krapan, without even knowing about Yao's long-held conjecture, ended up inventing a new kind of hash table that didn't rely on uniform probing at all. Instead, his design uses a different approach, and the result is astonishing. The time required for worst-case queries and insertions turns out to be proportional to log x2. That's a huge improvement over the old x-bound. In fact, when William Kussmaul from Carnegie Mellon University saw Andrew's work, he said, "You didn't just come up with a cool hash table, you've actually completely wiped out a 40-year-old conjecture." And that's exactly what happened. But the surprises don't stop there. Yao's original work also tackled the average query time for hash tables. For so-called greedy hash tables, where a new element is always placed in the very first available slot, Yao showed that the average query time couldn't be better than log x. Andrew and his team, however, explored non-greedy hash tables and found something extraordinary. The average query time in their new design is constant, meaning it doesn't depend on x at all. So why does this matter? Even if these results might not lead to immediate practical applications, they completely change our understanding of one of the oldest and most efficient data structures in computer science. By challenging decades of accepted wisdom, Andrew's work opens up new possibilities for optimizing how we store and retrieve data, a discovery that could eventually lead to faster, more efficient systems in the real world. Thanks for watching, everyone. If you enjoyed this breakdown of a game-changing computer science discovery, be sure to hit that like button, subscribe for more deep dives into tech breakthroughs, and leave a comment below with your thoughts. I'll see you in the next video.